Hi, I'm Nidhi Pandya, and this is my Lab 5 presentation on Faraday's Law. The overall purpose of this lab was to use Faraday's Law to relate the magnetic field of a falling bar magnet with respect to time to an electric field around an aluminum solenoid which could produce a current. We'll see that this current produced a magnetic field which exerts a force on the source of the external magnetic field. For the experiment, we dropped a bar magnet through the center of a roll of aluminum foil, which acted like a solenoid, and recorded the time it took to fall all the way through the solenoid. And this was repeated in 3 different orientations. And then I also created a computational model of this experiment using VPython and compared my experimental data to the computational model, and the results were that the magnet in my computational model took about 3 times as long to fall through the aluminum tube than the real magnet took. Some of the most important physical concepts employed in this lab were Newton's second law, which states that the net force on an object is the product of the mass and acceleration of the object, the Biot-Savart law for a current-carrying wire, and the equation is shown below. Faraday's law, which states that a change in magnetic flux in a circuit induces an electromotive force that is directly proportional to the rate of change of the flux. And as stated in the introduction, I use this law to relate the magnetic field of the falling bar magnet with the curly electric field around the solenoid. And finally, Newton's third law: for every action, there's an equal and opposite reaction. In this lab, it's for every force, there's an equal and opposite force. For the actual experiment, we had 3 different orientations of the bar magnet. The first one was the south pointing upwards, the second one was the north pointing upwards, and the third one was there was no specific orientation. And so we conducted 10 trials and recorded the amount of time that the bar magnet took to fall through the tube, and all the values are shown in the table, and they're all in seconds. After I conducted my experiment, I created a computational model of the velocity of the bar magnet over time. Here I show a snippet of my code to calculate the change in flux over time. So first I inputted all the initial conditions that I also used in my experiment, and then I calculated the magnetic field at the location R relative to the magnet. And I found that the change in flux over time through each ring while the magnet was falling. Next, I used Faraday's law to calculate the induced current in the solenoid, and then the Biot-Savart law was used to calculate the force on each current-carrying ring. Then I used Newton's third law to calculate the force on the magnet by the current-carrying rings and calculate the net force. Finally, I used Newton's second law and I calculated the velocity and position of the bar magnet while it was falling and used that to create my computational model. So in conclusion, on the previous slide in the model, the coloring on the tube indicated the magnitude of current flowing through each ring. The red indicated clockwise current and the blue indicated counterclockwise current. And my model only showed red because the current that was induced through the tube was only clockwise. In my experiment, I also flipped the orientation of the magnet a lot, and I found that the dynamics didn't really change, but the magnitude of the magnetic force changes, and it took longer for the magnet to fall through when the north pointed upwards. Compare my computational model versus real life. I found in the real world, the magnet fell 3 times faster than what my computational model predicted. And after tinkering a little bit with the code, I found that if I decrease the mu that I chose, then it comes closer to the real world system values. The shape of my velocity versus time plot tells me that since it's very consistent, the net forces on the bar magnet equals 0. And then if I reduce the resistivity close to 0, the dynamics of the falling magnet would change a little bit, and the time inside the tube would probably increase. Finally, if holes or slots were cut into the tube, this would affect the ring currents because the area on the tube would be smaller, which induces less magnetic force. Thank you for listening, and my email is at the bottom if you have any questions. Thank you.